Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So after the conclusion, I'll give you a little bit of background on the university work and then say something about the market that's developed and what some of the technology challenges are to address that market. And there's just a couple of applications that we've done at Dust, and then open research problems, and that's actually in the conclusion. So I'll start there. So the good news is that there really is a market here, which is something that as an entrepreneur, 2003 and 2004, trying to build a company in this area, there was a lot of question as to whether there would be a market, and if there was going to be a market, when would it happen. And I think it's probably questionable whether we hit 100 million total revenue, I mean, for all of the wireless sensor networking companies combined in 2006, but it'll be at least approaching that number. And I think that we'll have something like a half a billion 5 years from now. I think with confidence we can say that that's going to happen. So that's a big, whether or not Dust Networks ends up doing something there, or Crossbow, or who ends up being the winners, I think there'll be multiple ones. The good news is that the field really is going to have a real market driving it. And with the exception of the great work that's been done by the people in this room, largely the academic community has, if anything, had a negative impact on the adoption of this technology in building and industrial automation, and even arguably in home automation. And I'll talk more about that later. We sort of missed the boat and went so far beyond what people were looking for, and kind of neglected some of the key problems early on, and I think that's really cost us, unfortunately. So some of the open problems that I would like to see people address that have to do with what I call academically dull applications, which are the ones that are making this future billion-dollar market. I'd love to see people talk about metrics for reliability and power consumption in these networks, coming up with, as Feng was alluding to, some standards, some definitions, some canonical problems. What is it that most people are trying to do in this space, and how can we judge whether we academically have done a good job of addressing those things? And then once you have metrics, of course, then you can start talking about optimal solutions. And there will be lots of different optima in this space. But that I think is the single most important thing that the academic community could do. And I'll say a little bit more about what I mean by that. My personal view is that when you start looking at optimizing those things, that you'll need tight time synchronization. And that's across an entire network, having the entire network operate in a, well, what from a sensor or from a wireless sensor network perspective is tight time synchronization, somewhere between, I don't know, microsecond to millisecond. I think also that sort of the responsible opposing viewpoint should be, why do all of this low power, low data rate, constrained environment stuff when Wi-Fi mesh is coming? And there's a whole chunk of this community that is arguing that what you need is a heterogeneous network, that you need a two-tier solution, that you have a powered infrastructure that you plug in, and then you have the low power sort of leaf nodes that take a single hop into that powered infrastructure. And if you're going to do that, for heaven's sake, do it with an ARM processor and a Wi-Fi node. Don't do it with an 8-bit microprocessor and an 802.15.4 node, because the cost of those two nodes is essentially the same. So that, I think, is a worthy thing for people to be working on. And then there's this really probably mostly dull problem from an academic perspective, which is, how do you decide as a new moat entering into the world of 2010, where there are 30 networks that you can join when you wake up. How do you decide which one to join, and how do those networks decide which ones to allow you to join, and so on? So I'll talk a little bit more about all these later on. So, and I just put this in, I think that the grand challenge, if I were going to specify a grand challenge in wireless mesh networking for sensors, it would be getting data from A to C in a multi-hop network reliably at low power. And that, I think, this community has largely just completely punted on. That's such a dull thing to talk about that there's very, very little research on that. Okay, so a couple of slides on background. 97, I wrote a proposal with Joe Kahn and Bernard Bozer on doing a millimeter scale wireless sensor node. $1.4 million, and 5 years later, we had this little guy on the nose of Lincoln, and that actually did have in a 5 cubic millimeter package had all the pieces that we wanted. It had sensing and computation and communication and power, all the 4 elements in something about the size of a grain of rice. And it actually did transmit that data, as Feng mentioned, optically. This is a little MEMS corner cube retroreflector, and it had a little photodiode right there, so you could talk to it with a laser at about a megabit per second, and it could talk back at about a kilobit per second. And that was a lot of fun and a neat MEMS project, and actually got us going on doing ultra-low power circuits, which I think was quite useful. But the most important thing about that is that I had 2 graduate students, Seth Holler and then James McClurkin, who did master's theses doing off-the-shelf wireless sensor nodes. And that got David Culler interested. And that, I think, is what was probably the single most important thing that I did. That, this new hardware platform, David looked at it and said, hey, that sort of fits with this. Randy Katz was involved in this Endeavor project we had at Berkeley. Next generation computing platform, let's write an operating system for it. And in sort of standard Berkeley form, put everything on the web, and things just took off from there. And most of you know more about this story than I do, actually. So lots and lots of neat demos. All of these, interestingly enough, in 2001, which is a little frustrating to me. And the thing that got me out of the university was we did all these wonderful demos, and I had a stream of people coming to my from GE and Johnson Control and Honeywell and Siemens and Invensys and Emerson, all of them saying, boy, that demo you did there or there or there or there, whatever it was, that's great. That's exactly what we want. How can we get that? And the answer always was, well, you can't. Put a sort of PhD level computer scientist on the problem and get some hardware and download the software, and a year or 2 later you'll be publishing your own Mac algorithms papers, and the applications aren't going to happen. So that's what led me out of the university to start Dust. I wanted to be able to give people a box and have it just work for a wide range of applications that they wanted to do. Okay, but the good news is that all this churn and exciting demos that we've done in the university academic environment caused a lot of stir in the market. And we have a sequence of interesting predictions made in the 2003 timeframe by the industry analysts. So you see down here, this is the number of Wi-Fi chipsets that were expected to be sold. This is the number of cell phone handsets that were expected to be sold. And this particular group was predicting that the wireless sensor network market would cross the cell phone market at just over 700 million units shipped per year in 24 months from now. So, of course, that didn't happen, but that's what industry analysts are paid to do. Let's say we'd be somewhere around 300 million a year right now if that were going on. So that didn't happen. But what is it that got everybody so excited? It's, if we kind of bring it back and think about from the the industrial-based perspective, this industry down here, the sensor world, is tens of billions of dollars worldwide just for the physical sensors themselves, the hardware before it has gotten into any kind of a network. And the world is filled with sensor networks, by the way. They're almost all wired today, and they feed information into decision systems up here. And this business up here, where the GEs and Johnson Controls and Honeywells and Emersons and everybody else play, that's beyond tens of billions into the low 100 billion kind of numbers for annual revenue. And today, those two industries are connected with conduit. Right? This is copper wires running in extremely expensive conduit, typically in buildings and factories where the cost per foot of installation is just staggering, far, far greater than the cost of the sensors. And in fact, in most cases today, far, far, far greater than the actual hardware cost of the decision systems that they feed. So this is the limiting bottleneck, and that's why the industry is so excited about it. So another industry analyst, also from 2003, and this one is for low data rate wireless personal area network chipsets. And this is component revenues for those, and this is in millions of dollars. So this is roughly 2003. And the important number to look at there is this one in building and industrial automation. That's this color in here. And in 2003, they claimed that the revenue there was $750 million. And that one, I don't know if that's exactly right, but that's actually pretty close. Because talking to all those companies that do this industrial automation, every single one of those companies has a wireless sensor product. And for all of them, it's a niche application. It doesn't have the reliability that they need to do the things that they want. But there are some places where it's just, the economics are so compelling that they sell into those applications. So there's a sort of, and in each one of those companies, it's $50 or $100 million a year business for them, and so sort of unimportant thing. And you total it all together, certainly talk to enough people to know that at least half of that number really is real. So that's what's out there today. It's these star-connected, point-to-point, master-slave kinds of networks. And that's growing at some healthy, 6% per year kind of rate. And the thing that's exciting is that potentially, if we can change the wireless sensor networking equation from being these unreliable sort of short-range solutions to something that's much more reliable and mesh-like and low cost to install, then you can imagine starting to increase on that billion-dollar industry. And I think this line is probably more realistic in terms of how the market is really taking off. I think in 2005, the revenues of all the wireless sensor networking companies out there, the mesh companies, is somewhere between $10 and $100 million, probably closer to the 10 side than the 100 side. And I think, like I said, next year I think we might, maybe we'll get within scratching distance of 100 million. But this is, the good news is that you don't have to grow to an $8 billion market by 2007 for this to be a very successful story from a technology transfer perspective or an entrepreneurial perspective or a venture capital perspective. So that's the good news. So and one last thing on this, what is it that these guys are thinking about? If I'm thinking about the cost of a sensor network from a building automation or industrial automation perspective, the cost of the computing power is just going down dramatically. The cost of sensors is falling, maybe not exponential curves, but certainly over time dropping dramatically. Unfortunately, if anything, the cost of installation to date has been going up, right? These are labor-intensive and in some cases equipment-intensive operations. And so the reason that everybody in the industry is excited is that we have the potential now with mesh networking of getting off of these kind of labor kinds of curves and onto more IT kinds of curves. Okay, so of all of that, the most important thing that happened from my perspective was the creation of this Zigbee industry consortium, because that got a bunch of the end users together saying, if you build it, we will buy it. And that's what got the venture capital community moving and what saved my little company, and we finally managed to get venture capitalists to invest in it. You can see that there's Zigbee has a pretty wide range of things that they're interested in going after. This is my particular favorite, zigbeef.com. This is a real website. I think it's actually more RFID, but it's nonetheless a fun animation. So, a bunch of companies out there. This is actually a subset. Several $100 million in venture investment in this space now. Where's Dust fit in? I started this in July of 2002. Ended up raising about $1.5 million from angels. We finally closed a Series A 14 months later, and I managed to kick myself off out as CEO and become CTO where I should have been. And we closed a Series B earlier this year. Total of about $30 million we've raised. And what was it that I? It's a little risky to say set out to do, because as I was saying to Deborah this morning, I have actually no recollection at all of what I was thinking when I left the cozy womb of academia to go off and do this company. But certainly somewhere pretty soon along the way, what we realized is that what we needed to do was make networks that were high reliability and low power consumption and did not require our customers to write even a line of code, or in fact even allow our customers to write a line of code that ran on the moats. And to do that in an environment where you've got resource constraints and nasty interference is sort of the challenge. So what led us to that? Well, as we went out and started talking to OEMs and system integrators, what we discovered was that what they wanted, really the top three items of what they wanted, were reliability, reliability, reliability. It just didn't matter. They could be free And they weren't going to put them into their products unless these things were extremely reliable. And they're looking for reliability comparable to wires. They're just not interested. The companies in the building and industrial automation space, and some of these companies have had customers for a century. And they don't want to lose them because they put in a bad product. So once you've satisfied that, then they're willing to start talking about, well, you know, it's got to be cheap to put in and it's got to be cheap to own. And what that means is that you can't run power to it, and you can't be going out and changing the batteries on a regular basis. And you can't, you know, this is not sort of IT kinds of applications and IT infrastructure. So you can't have experts going out and doing your site surveys and network management and stuff like that. So those are you know, that is really challenging. The good news is, and I think the reason why the academic community has really kind of ignored this stuff up here, is that the data flow from these applications is really, you know, kind of dull. They want to put out 50 sensors or maybe 5,000 sensors, but they want to put out a bunch of sensors, and they just want to get the data back once every hour, or maybe once a minute, or maybe once a day. I mean, it varies, and there are certainly applications where it's faster than that, but that, you know, minute to day sample rate is by far, that captures the vast majority of the things that people are asking for in that community today. And if they have latency issues, so they want it less than a minute, maybe they want it in seconds, then in general you're not talking about regular data collection, but rather talking about some kind of alarming function. So, you know, in terms of data flow in the networks, really trivial compared to the kinds of you know, incredible demonstrations that have been done in the academic community, funded by DARPA, right, to do totally different kind of application. And the thing to note, you know, that when I sort of think back on it, you know, why did I leave the university? It's because I had, you know, people from biology and people from civil engineering and people from mechanical engineering who wanted to get access to these networks as well, and I couldn't help them. And so, you know, what do they want? Well, they really want reliable networks also. And you know, I think certainly the last time that Deborah and I did a tag team, that was one of the hallmarks of her presentation as well, that reliability for scientists, you know, they care about this stuff. The people who are using the networks want them to be reliable. So I think that it really doesn't matter who you're talking to. They'd like reliability, and most of them would like low power operation, and most of the applications really don't have very demanding bandwidth kinds of constraints. Okay, so a word or two on reliability. In terms of the hardware, you know, there's some you know, painful realities that you have to deal with when you're going, especially minus 40 to plus 85 centigrade, and you know, back and forth on that. The kinds of reliability numbers that people are looking for on the hardware are, you know, I want to put out a 50-node network, and I want, on average, to do one truck roll per decade on that network to fix the hardware. And so, you know, that turns into a mean time between failure per mote of 5 centuries. And the good news is that if you're careful about the way you design and build these things, that with best practices you can, in fact, sort of do the certification that shows that you will have an MTBF measured in centuries, more than 5 centuries, actually. On the software side, we decided to go with Linux as a very stable and reliable embedded environment, and we decided not to go with TinyOS. And the reason there was that we figured that if we were going to, you know, we wanted to leverage this, you know, exciting, fast-moving community out there, but what we were going to need to do was we were going to have to take a snapshot and say, okay, this is the snapshot. Let's fix all of the bugs in this and support it ourselves, and then the community would be moving on, and we'd sort of be, you know, watching them, but well, we're kind of stuck back at this old version and would not have the ability to make that transition. And so we decided that if we were going to be in that position, we might as well just do our own operating system. So, and the real challenge in reliability from a networking standpoint is the interference and multipath, and I'll have a couple of slides on those. So, if we look at the 802.15.4 radio spec in the 2.4 gigahertz band, there are 16 channels here, and if the area of each one of these channels that are little mounds that I've got there represents 1 milliwatt, which is a typical transmit power for one of these motes, then a Wi-Fi node looks something like this. And so the idea that you are going to spread spectrum your way out of interference with Wi-Fi and cordless phones and things like that is just wrong. And it's disingenuous of the people in the Zigbee community that are saying this, because you'll hear people say, we don't have to worry about interference because we're spread spectrum. And it's just not true. You can't spread your way away from that. One example, here's a 900 megahertz example. This is a spectrum plot, from 902 to 928. That is the ISM band at 900 megahertz. And this is power here. So this is 1 milliwatt up there, a tenth, a hundredth, a thousandth. So this is about a microwatt right there. And with a narrowband receiver, you need something like 10 dB of signal to noise on top of that. If this were a spread spectrum, sort of Zigbee style spread, or 802.15.4 spread spectrum receiver, that line could be more or less right on the envelope of the noise from the cordless phone. But essentially, that red line tells you how much power you need to have in order to burrow your way through the interference and get your signal received. So you need to be above the red line in order to be heard. And the problem is that that little line right there is a very healthy mote signal. Right? Minus 50 dBm is, it gets better, but not a whole lot better in this world. And so what that means is that at least in the 900 megahertz band, this cell phone has wiped out, or cordless phone, excuse me, has wiped out basically 60% of the band. And if another person with another cordless phone turns theirs on right next to it, then you're going to jam some other piece of the band, and they'll quite possibly hop their way or move their way so that they're not interfering with each other. So that means they're going to interfere with you. So interference is a big deal. Now, multipath is another one that is really painful. This is some data from my friend and arch rival Rob Poor, formerly from Ember, founder of Ember. He took a couple of motes and put them at reasonably extreme range and put one of them on an XY table and moved the one on the table by a wavelength in X and Y in 10th lambda steps, and then measured what his signal strength, or rather, excuse me, what his packet reception rate was. And the interesting thing here is that you see this valley of death inside there, and that has to do with just random reflections off of desks and filing cabinets and doors and so on. And all you have to do to completely change that picture is move a filing cabinet, move a chair, walk through the environment. And so this kind of way sub-wavelength variation in the RF signal strength gives you a huge challenge in terms of building reliable networks, because there is no such thing as a static RF environment. You have to be prepared for something moving in the environment, and all of a sudden a signal that was perfectly strong here, 1 centimeter away, and you get no packets. Another good one. This is Jay Werb from Sensicast and GE, looking at received signal strength as a function of frequency in the 2.4 gigahertz band. And you can see variation here from minus 50 dBm to minus 100 dBm, depending upon what frequency you're on. So 5 orders of magnitude difference. And if you smooth that out with a 2 megahertz bandwidth, maybe you only end up with 20 or 25 dB of variation. But you're talking orders of magnitude difference in signal strength due to multipath, depending upon what frequency you're on inside the band. And this changes on a regular basis as well. So RF is nasty and unpredictable, and I can't say it, or I'm too cautious to say it in words in the presentation, but I can tell you that stuff like this from Wireless Valley is just complete bunk. And there's just think about the kind of speckle that you'd need on this 50,000 square foot floor plan there to represent this kind of path loss, right? I mean, there's just no way that in this whole region in there you're going to get minus 70 dBm, and here you're going to get minus 60. Baloney. And so, I think that these kinds of simulators for RF connectivity should be treated very, very suspiciously and cautiously. I think they're almost worthless in terms of predictability. Okay, so what do? Well, ultra-wideband could be continuously promising, Still haven't seen evidence that this is going to solve our problem, especially in terms of being able to turn it off when you need to turn it off, and then turn it back on again quickly. So direct sequence spread spectrum, good. So 802.15.4, very happy to take that 10 dB that you get from spreading. That's a good thing. But that's clearly not enough when you're in an environment with 1 watt transmitters. And having plus 20 dBm, putting out 100 milliwatts like Wi-Fi does. But we know that that isn't enough, right? Anybody who had an 802.11b system and bought a cordless phone and had to either buy a new phone or switch Wi-Fi or whatever, it's not enough just to have a factor of 100 more power. So really the only solution, I mean, you can do as much of this as you want. These things are all helpful. But you really, even if you do all of that, you still really need to frequency hop in order to get the reliability that you need when you're in these ISM bands. So, and if you're going to frequency hop, that means somehow the receiver and the transmitter need to know what time it is. They need to know what frequency they're going to be on in some generalized sense at the very least. But you probably needed that anyway, because these samples that you're taking, that you're delivering back to an application, aren't being taken in a vacuum, right? These people need timestamps on their data, so you've got to do some time synchronization anyway. And once you've said that you're going to do that, then all of a sudden you get the entire band. The scaling problems become a whole lot less painful. The interference problems, all sorts of stuff gets a lot better as long as you're willing to frequency hop. So I'm pretty fanatic about the need to frequency hop, even if you're doing direct sequence spread spectrum, even if you're doing plus 20 dBm transmitters. Okay, so how about networking and routing? Well, the traditional way of doing this is you have your one powered infrastructure node and you have battery powered nodes that take a single hop back into that powered infrastructure. And this is what's selling at something like $750 million a year, whatever that number actually is. And the reason why this is not reliable is that all it takes is one filing cabinet or one door to move, and you've lost your signal strength between these two things can go down by orders of magnitude. So it doesn't matter how much site surveying you do, you're always susceptible to losing one of your nodes that way. So next step, StarMesh. This is from the Ember webpage. You make a mesh infrastructure which you plug in, and then you can get multi-hop and multiple parents and so on in there. So you've got lots of paths, and then you just take a single hop into that infrastructure. Well, the problem with that is that if you look at the top 4 modes here, they're identical to the top 4 modes there, and you still lose that path. You've still lost your reliability there. But the real puzzle for me on this is that if you're going to plug in your network, then why in the world would you not use 802.11? Because you absolutely, you can build an 802.11 network like this and have battery-powered nodes that wake up, squirt in a packet, get their response, and turn off again, and burn the same amount of charge out of the battery as an 802.15.4 mode does. The radios burn more power when they're on, but they're on much, much shorter because of the bandwidth difference. So anyway, so that I think is a very valid approach to wireless sensor networking, and is in some sense very much a competitor to what I think the right solution, if you are going to be battery powered, is that every node in the network has to be able to mesh with all of the neighbors that it can hear. So a word on Zigbee. This is where I really the academic community, we really did not get involved early on in this, pretty much at all in this standard, and they made some really big mistakes in my opinion. So single channel networks are just built into the standard. I will build a network on channel 3. Those of you who can hear me will build the network on channel 3, and it'll propagate like that. If there's a group in the back of the room that can't hear channel 3, I will never know they're there. They will never know we're here. And that's that. And if somebody comes in and jams channel 3, our entire network collapses and we have to rebuild it on another channel. So basically all of the major building and industrial automation companies now have concluded, and most of them have concluded publicly, that Zigbee 1.0 is not going to cut it for industrial and building automation applications. There's some neat, some clever node numbering things and so on to do tree-based routing in the protocol, where just based on your ID you can tell sort of where you are in the tree. The problem is it's a tree, it's not a mesh. And in the Zigbee 1.0 standard, it specifically defines a mesh as a multi-hop network. And I think we're all familiar with what a mesh really is, right? It's sort of connectivity like that. If you try to take a nap in a hammock that's made out of a tree, you fall through, and so will your data. So we know what meshes are. They aren't trees. And this, the good news is it doesn't explicitly prevent you from duty cycling your routers, but it's not in there as well. And so in terms of compatibility among solutions, that's going to go away. So maybe perfectly okay for home automation kinds of things where it's okay to plug in your routers. You plug in one in the kitchen, in the garage, in your bedroom, fine. And reliability isn't so important, but not for much else.
What's the difference between adaptive trees and a mesh?
I don't know. What's an adaptive tree?
So
As long as I have an option without having to sort of rediscover routes to send my packet somewhere else, if my connection to you goes down, then I'm happy to call that a mesh. It's perfectly okay to have sort of this is the best path, and that's the one I try first, as long as I've got some flexibility in how I send it without having to go into a mode where I say, well, I've lost my connection to the network. Is there anybody out there who can hear me? Right? That's the situation you don't want to be in. Okay, so here's my take on power optimal communication. What is it that we need to be able to do in terms of sending a packet from B to A? And I'm just sort of starting off with the assumption that we have time synchronization in this network that's accurate to a fraction of the length of time that it takes to transmit a packet. So, so A and B have agreed on some schedule that they're going to communicate on, and so when A knows that B is about to transmit, it wakes up a little bit early based on the worst case clock skew between the two, and it stays awake a little bit late. And if it doesn't hear the start symbol from B in that time period, it just goes back to sleep, because it means either B didn't have anything to say, or for whatever reason the signal was jammed, or multipath, that channel is dead, whatever it is, the start symbol didn't get through. There's no reason for A to be awake. If the start symbol does get through, then as B transmits its data, A stays awake, and then they turn around and A transmits an acknowledgement and B receives the acknowledgement. At that point, B deletes the packet, and now it's A's responsibility. And so I would argue that that's sort of the minimum amount of energy that you need to get a packet from A to B. And as you get more and more accurate time synchronization, you can make this window get smaller and smaller, which has some benefits for latency. So here's a picture of current consumption versus time for a typical radio. This is a CC1000. There's a startup time period, so there's some energy that you have to pull out of the battery just to get the radio spooled up and going. Then there's the time that you're actually doing the transmission. There's a little bit of energy associated with turning around from transmitting the packet to going to receive the acknowledgement. And then finally, your ACK reception. And if you sort of integrate all that up, you find that in this particular radio running at 76.8 kilobits per second with this packet length, blah, 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 you get around 300 microcoulombs. And so now we know, that this is sort of the lower bound for this kind of communication. If I know that I have a node at some point in the network and it's going to receive so many packets or transmit so many packets and there's perfect time synchronization, then I can calculate what my power consumption has to be depending upon how often I'm sending and receiving and so on. And the answers there look pretty good, even with today's radios. They're, for typical applications, they're in the tens of microamps to maybe low hundreds of microamps. So I'd also like to be able to, as I said, A is going to wake up and listen periodically, and if it doesn't hear anything, it just goes back to sleep again. And what does that cost us? So again, there's the receiver startup time, there's the time that it spends listening. In this case, I think it's 5 milliseconds, and then it goes back to sleep again. And so that costs, in this case, 70 microcoulombs. And so that lets you talk about reducing latency and what the cost of reducing latency is going to be. So, or providing redundancy in terms of communication bandwidth in order to deal with interferers and path loss and so on. So A is waking up periodically and going back to sleep again because it's not hearing something from B. Maybe that's because B doesn't have anything to say. Maybe it's because B is being jammed or the channel's bad or whatever. At some point, they wake up, B has something to say, the packet gets transmitted and acknowledged, and then they go back to the same game again. So what does it cost us to have this extra bandwidth in there to deal with interference, path loss, or excuse me, multipath, and latency reduction? Well, I know what my listening energy costs. I know how often I want to do it in order to get my latency, and I can come up with how many microamps that's going to cost me in addition to the fundamental amount of current that I need to pull out of the battery in order to do the communication that I've got. And again, that number is respectively low for most applications. So, so that was all a single hop in this. Obviously, we're making multi-hop networks. We'd like stuff to flow up the network in sort of peristaltic networking kind of way. So you take all of the ordered links going back to some central node or doing whatever data flow you want, and you call that a superframe, and that repeats in time. And you need to take your directed graph that you've drawn to represent what the connectivity looks like and map that into a time and frequency matrix. And so each one of these links here goes into a particular time slot and at a particular channel offset. And then as you repeat that in multiple cycles, n plus 1, n plus 2, the channel offset plus the cycle number modded by the number of channels gives you the actual channel that the motes are going to communicate with each other on. So you end up with quite a big matrix here. You've got hundreds to maybe several thousand cells per second that can happen simultaneously in the network because the channels are independent and the time slots are independent. So there's a lot of bandwidth that you've got to work with there. And when you're all done, this is stuff that we did at Dust. This is 50 channels in the 900 megahertz network. You see we keep the FCC happy on the borders, and we filled it in. That's good spectral usage, right? That's what you want to see to show that you really are using the whole spectrum. This is with the 802.15.4. So these 16 little humps in there are the direct sequence spread spectrum signal from the 15.4 radio, which we hop in addition to the direct sequence spread spectrum. So, what did we end up with? Our motto pretty early on was configure the network, don't compile code. So we neither encourage nor, in fact, allow people to write code that runs on the motes inside the network. We have one powered node. That's the manager. It's a little Linux PC. And you plug that in and to Ethernet or a serial port, and you speak XML into it. And you configure the network. You say, I want these guys to sample once a minute and report if they see an alarm threshold, blah, 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 and these guys are going to do something different. And we take care of all the management inside of that. And so you can write, very easily write applications up here that speak XML. And the set of people on the planet that can competently write XML is substantially larger than the set of people who can competently write embedded code for doing multi-hop mesh networking in a resource-constrained environment. So what kind of performance did we end up with? We talk about reliability as, of all the packets that are generated in the network, what fraction of them pop out the XML port to the application. And we started off speccing that at 3 nines. Now we're speccing it at 4 nines. And the average current consumption of all the nodes in the network is less than 100 microamps for a typical low data rate application. So here's a picture of our console. There's the manager in there. And this particular network was at a printing press nearby our office. It's 50 motes, 7 hops deep. It's about 150,000 square foot facility with lots and lots of rotating machinery and multi-story printing presses and things like that. The network's generating about 100,000 packets per day. And if you go up and click on our network statistics tab, we bookkeep what the path stability is. This is the daily average. We could get 15-minute averages. And these are typical, I think fairly typical numbers for these low-power radios. 80 to 90% is the hop by hop. Of all the packets he tried to send on this link, what fraction of them got through on the first try? And then we also bookkeep the data reliability. And this is the end-to-end, of all the 100,000 packets per day that are generated, what fraction of them popped out that Ethernet port right there. And there you can see, 4 days where we didn't lose a single packet and, lost 1 there, 3 there, 2 there. So this network's running at around 5 nines reliability. And actually, we know what's causing that. It's the CRC, actually. Random bit errors in the packet that don't give me an invalid CRC, right? If I've got multiple bit errors, sort of 1 in 2 to the 16th times, I still get a valid CRC. And so somewhere in the network on one of the hops, I accept that packet and say, yep, that's a valid packet. but by the time it gets to the manager looks at it and says, well, this doesn't make any sense at all, and throws it out. So that's why we're at the point where it's the multi-bit errors in the CRC are giving us trouble. And this is a 1 week kind of number. Yeah. So this is average across the whole network. We can give you, for that mote on this path in any 15-minute interval for a week or a day, week, something like that. Lots and lots of information in there. We don't build huge networks from a single manager. The spec is 250, so there's clearly we need to work on our display. But one of the nice things about it is that you can manage lots and lots of networks in the same place. So we have, I don't know how many thousand motes running in our facility at DUS. This is a small subset of the number of networks that are there. And so you can, from anywhere in the world, go in and check out what your networks are doing.
Bring up a second manager to create two.
Yeah. So, meaning, each one of these lines is a different manager. I can have multiple views going in and looking at the same multiple managers. I can have multiple managers. They will build separate networks. So if I can have two interpenetrating clouds, and in fact do. All these are basically interpenetrating clouds.
How configured or automated is that? So if I plug in another manager, then we're within this range of the cloud.
So
I don't even know if you want it to be automated.
right. Oh, yeah. Everything wants to be automated, right? The question is, how magical can you get, right? How can you magically decide which mote should join which manager? So right now, the motes are programmed with a cloud ID, and the manager is programmed with a cloud ID, and they have a network password, and so they will only join, and the managers will only allow them to join if the cloud ID and the password match, which is not optimal.
Another manager with the same cloud ID comes up.
Right, and in fact, that's fine. We've done that. So you put another manager in there. Once the network's built, the manager will come in and nothing will happen. But if one of them fails, then the other one it'll build onto that manager. And they can, if they come up at the same time, you'll end up with an interpenetrating cloud that goes to the two separate managers. Okay, so what is the communication abstraction? So packets flow along directed graphs, and they're colored if you want to think of them that way. And so you have black packets that flow on a black graph, you have red packets that flow on a red graph, and you get to set what the period is over which these links operate. So the black graph may be a 60-second period, the red graph may be a 0.5-second period because that's a low latency, you want that to happen really fast kind of thing. All the atomic operations have known properties, energy in particular. And the good news is that simulation of things like capacity and latency and everything else matches very well with what we actually deliver. So it's very easy to predict what the performance of a network will be given certain kind of interference and so on. And similarly, if you see certain performance in the network, you can simulate it and see what's actually that goes both ways. And you can, there's sort of the default, just let us create you a network that gets data back to some central location. Or you can go in over XML and say, I want to create a graph down here with a period of, 500 milliseconds and have certain links on it and so on and do all that. And we give you, to sort of answer your question, give you lots of information about all the connectivity information in the network, all the packet attempts and successes and CRCs and everything else, latency, ... and it's just, also more data than you want. And that's just basically to convince people that this network really does what we claim it does. Because all of the companies that we go into have been burned by wireless before. And they're all extremely skittish about trusting it.
So what do you do when nodes fail? Do you reconfigure the network on the fly? Or
What do you do when nodes?
nodes fail?
When nodes fail. So they don't in general. But paths fail because doors close and things like that. So there's path redundancy in the network. So every node has at least two different parents. And so when a node fails, that gets detected because the sort of heartbeat communications aren't happening anymore, and the additional connectivity gets pushed down into the network. Today the network is managed from that manager. All the connectivity information or communication path information is done on the Linux PC and pushed into the network. So today you can go in and knock out big chunks of the network, pull their batteries out if you want to, and anything that's in there will generally continue to communicate at high reliability. Power consumption will go up, but then as more links get pushed into the network, it returns to a safer state. Okay, so configure, don't compile. There's a configurable data filter layer in there where you get to set things like, I want to sample on channel 3 once every blah, blah, blah. I've got some threshold. Don't report unless you see a value go above something, and then give me the last 6 samples, stuff like that. Some of the applications that we've done, this one that we did at Honeywell, this part of Honeywell doesn't exist anymore, but they used to go in and monitor power consumption in grocery stores, and so they would have an electrician go out, pull the panel off of this box, and snap a current transducer around each of the high power lines going off to chillers and air conditioners and lighting systems and so on. And then traditionally he would run conduit back to a central box, which would then call that information into Honeywell. They'd analyze it and sell it back to the grocery store to reduce power. In this case, he still unscrews the thing, snaps the current transformer on, but now he just screws in one of our motes, plugs in the sensor to that, and then plugged our manager in next to the Honeywell box, and got the whole network in 3 hours. And it's been running. This is the only really interesting part about it. This has been up for 12 months at 4.9, better than 4.9's reliability. I guess the other thing that's interesting is this is a trained, licensed electrician. He had the panel of the power box open, right? And Honeywell has worked the numbers that say it is still more cost effective for him to put in a battery-operated node there than it would be for him to screw in another box, pull a piece of conduit 6 inches, and run wiring, put in the breakers and everything else. That as long as the battery lifetime of the network is greater than however many years it is that they came up with, it's more cost effective for him to do a battery-operated network than pull power. This one is actually, I think, my favorite because finally, 4 years after Rob Shevchuk and Jason Hill put in this power and temperature monitoring network in Corey Hall to help Dean Newton sell the Citrus building at Berkeley, we finally got a real commercial deployment of the same thing. So Tritium is a building automation company that does sort of Ethernet, BACnet kinds of systems. So we plug into their box, and Tang is the system integrator, and they went in and put in a temperature and power monitoring network in an afternoon into this building, and it's a cinder block building, and the cost to have pulled wires in there was astronomical. I forget what they estimated. It's like 4 weeks it was going to take them to do that. And then my favorite thing is that it's their display and not our display now that this comes back to. So those applications were all done just using the configurable filters that were on our motes. You've also got a serial port on there. So for if you've got some kind of compute-intensive application down there, then you can stick your own sensor or stick your own microprocessor down there, to do whatever you need. And you get to use your own microprocessor and your own development environment. You don't have to share our microprocessor and our development environment to do that. So SISE is a company that's done that. They've got a little CMOS camera in there and a whole bunch of other sensors. They're doing, sort of again, 4 years ago we went to 29 Palms and detected things going across borders and down roads and things like that. They're finally actually deploying this on the U.S.-Mexico border. And then my other favorite one is near the U.S.-Mexico border at the Marine Corps Chocolate Mountain Gunnery Range. This is, let's see, where is it? Address a need to detect intruders, smugglers, and scrappers. So people come in and grab that stuff to sell for scrap. So the Marines do not want to create an international incident by bombing illegal aliens coming across the border. And then a fun kind of a next generation thing. This is a startup, Streetline Networks in San Francisco. They want to put a moat every 5 meters on every street in every city in the world and use that for all sorts of sort of urban stuff. And actually, Larry Page is quite interested in doing this as well. I had lunch with him a couple of weeks ago, and this is the kind of thing that he's interested in doing. And their first application for Streetline is parking enforcement. And basically the idea is you monitor when cars have exceeded their time limit, and then it's kind of like Pac-Man, right? You send your parking enforcement officers down the lucrative streets first to gobble up all the money from ticket revenue on the streets where they're going to make the most money, and you don't have them drive elsewhere. Okay, so finishing up, last couple of slides. This was a goal in 2001, was to do an entire moat on a chip, putting the sensors and front-end amplifier, ADC, memory, microprocessor, and the radio. And at the time, I thought that this could be done for 2 square millimeters, and that we would need basically just 4 external components to make that happen. And that given that size and these components, that you could actually manufacture one of these things out the door for something like $1. And that's a little optimistic. The 2 square millimeters is wrong. If you look, but there are chips coming out now from Ember and Chipcon and so on that really have all of this stuff on there. They're about 10 square millimeters today, typically in quarter micron CMOS. And very often they do have, the parts count isn't a whole lot different than what we're looking at right here. And the bill of materials for a moat today is on the order, well, it's under $5. For sure you can build a moat, the hardware side, for under $5. The chips, Chipcon is saying $3.30 in volume for their cheapest system on a chip. So their manufacturing cost can't be a whole lot different than $1 for that chip if they're selling it. This is some of the results that we had in 2003, where we did a bunch of system integration. I think the important part of that is really the radio. And if you look at radio receiver current in milliamps versus bit rate, this is the best 802.15.4 radio out there right now, 250 kilobits per second and a little under 20 milliamps. This is a 900 megahertz radio that we're using at Dust. And university results. So Al Molnar did a 100 kilobit per second radio for 400 microamps. Brian Otis did a 5 kilobit per second radio. Al's a student of mine. Brian's a student of Jan Rebais, who just went off and joined the faculty up here, actually, at UW. And then my student, oops, yeah, 2 other commercial offerings. Now who is that? Oh, that's the Ember chip. Ha! Gosh. Oh well. My student Ben Cook just demonstrated a 300 kilobit per second radio at 2.4 gigahertz that burns 330 microwatts in receive mode with sort of comparable data rate, comparable noise factor to the 2420 in the same band at literally 100 times lower power. So this is all good news. This is where the technology is going. There's the university research results today, and that will turn into chips in the next. It'll take a few years, but that's where things are going. What else is going on? So that was the radio, tens of milliwatts today, going down to hundreds of microwatts. Literally, die area for that is not really going to get down below a millimeter square unless something fundamental happens, because it's limited by inductors today, and that's not susceptible to process scaling. ADC is essentially zero power in area. We showed that world records, that basically take it off the table. Moats, I think, are going to have 32-bit microprocessors pretty soon. I mean, the age of the 8051 on a moat is going to go away. There's some nice low-power processors out there today that are less than a square millimeter and are heading down, figure in a 90-nanometer process to something like a quarter of a square millimeter. The crypto costs about the same number of gates as the processor today, and the power per megahertz is going down as well. These are sort of today kinds of numbers. Today, you get about a megabit per square millimeter for ROM and flash, and right now, this is the thing that's the most painful, actually. The memories are not designed to be run efficiently at these low clock rates. And that's straight, better circuits will make that problem go away. There's no fundamental reasons why that has to be. And this is actually an interesting point. When we're getting to these low power radios and these deeply duty cycled networks, the leakage current from the logic actually is more than the average power consumption of the moat itself. So that, again, turns out that there are circuit solutions. The processes are getting worse as we go to finer and finer line widths, but the circuit solutions are getting better. So here's my prediction, for where we're going to be in 09. Same stuff. I do think we'll be down. It will get down to something like 2 square millimeters. I think we'll have, the security, AES is already in there. I think you'll have support for ECC as well. Location information, RF time of flight location. My student's been working on that for a couple of years. He just got sort of 2-meter accuracy in brass board version, and I think support for very tight time synchronization will be in there. And I think the fun thing is that actually the inductor goes away at 2.4 gigahertz. That goes on chip. I think that we can get rid of the crystal, too. I think we can put the timekeeping on the moat itself. That's very much an open question. And Ken O at the University of Florida thinks we can put the antenna on there. There's no question you can do it. The question is what's the penalty to do it. And so I think in terms of fundamental limiting open problems in hardware, there are none. And we've gone down the list. We took. There are some sensors still that are fundamentally high energy per sample, but the vast majority of them aren't. If you do them right, ADC gone, microprocessor gone, radio basically took that off the table. Now ranging is demonstrated. This is going to work. We're going to be able to get meter accuracy on everything, and we're seeing commercially that all this can be integrated together. So I really think that there are no fundamental hard problems left on there. There's pushing the limits on how low can I get GPS, for example, but I don't think there's much there. On the software side, let me just say a quick word about security. We all encryption and integrity, yeah, but how about certification and binding? How do moats know how to join the right network, and how do the networks know to accept them? And if you put yourself a few years in the future where you've got lots of moat suppliers, lots of system integrators, and lots of neighboring customers, how does this new moat know which one of these networks in what building to join? And do it in a secure way, because the data from that network is going to be critical. And it has to do it at 3 a.m. when some high school dropout is the one who's going to take the new thing off the shelf and install it where it needs to go. So, open problems, in my opinion. Defining and getting good metrics for reliability and power consumption in these just boring, get data back to a central location kinds of applications. And simple models for interference and multipath and radio power I think are fine to start with. Let's at least start talking about what are the metrics to use in there. And you've got to be thinking at the bare minimum, 3 nines reliability is what you need to talk about. I think time synchronization is going to be critical in there. As I said before, I think if you're going to put in a powered infrastructure, make it 802.11, and I think that's a worthy area of research that I haven't seen anybody really look at. What happens if you try to deeply duty cycle the endpoints in an 802.11 network, and then this how does a moat identify itself? And the answer is public key, almost certainly elliptic curve. How does it then decide to bind? Which one does it bind? How do you commission the networks and so on? And then finally, I think there's one more layer now. How do I make it even easier for people who have good ideas to get a network up and running and get the data that they want? And putting it on the web is a step in the right direction. Let's take that another step further and get it into the applications that they want, and get it into the wireless systems that they've already got, that they're already carrying around inside their pockets. And with that, I will thank you all for your attention.
Would you summarize the question for the recording?
So the question is, what if you need more processing for the sensor application? And I think it's a very valid question. There are plenty of applications where you need to do substantial signal processing on the sensor data in order to do whatever you need to do. My personal that end up doing the same thing that you do in other communication systems with computational capability, right? My laptop, you run the application on the processor for applications. There's a separate processor that runs the communication system. Same thing. And most systems are like that. So I believe that the right way to do it is that we optimize the communication processor to do the communication job, and you put a separate processor on there to do the computational stuff, sensor computation. But I'm willing to believe that if I can put a 100 megahertz 32-bit ARM processor on there for a square millimeter and give it a half a meg of flash and blah blah blah, that I can probably do enough on the operating system side that I can disentangle the communication piece from the sensor computation piece, because that's the fundamental reason for me, is that I've just seen so many smart people, both in academia and industry, go in and try to solve the application processing side while the communication piece is running. And it's a nightmare, right? I mean, that's why it takes years and years for people to develop applications right now. So So I guess that's not a fundamental problem. Easy to drop a 32-bit core on there to do your sensor thing. Yeah. So, but the cost is minimal, and putting another 2 square millimeters on there is literally, in low volume, it's 20 cents, right? A square millimeter for your processor and a square millimeter for ROM and flash, or flash and RAM. And if power is the issue, and you're at something like 50 microwatts per MIP in a 32-bit processor, and absolutely there's a couple of decades that show that once you've decided what your algorithm should be, putting that into custom silicon drops that by a factor of 1,000. So I just don't think that that's going to be a limiting factor for anybody. I think there's going to be great work done there, but for years there was, in my opinion, real question of God, can you do this at all? Can I put a radio on there and a microprocessor and an ADC and burn power that's going to be commensurate with a decade lifetime off a battery? And so I guess in terms of saying there are no hardware issues, I think I've sort of gone down the list and shown that I can do all of those things and still get a decade of lifetime off of a cheap battery. That's right. That's right. So to summarize the question very, very briefly is, so is there going to be control as well as sensing, and should that be optimized together? And the answer is absolutely. I do think that that's ultimately going to be the reason why people do that today. But it's going to take a few years, right? I mean, the caution associated with the adoption of this technology, just purely on the sensing side, is small compared to the caution that's going to be involved when industrial automation people start using it to do control, send control signals down. But I do think that will happen, and I think that local computation and local signal flow inside networks is going to be a big piece of that, and I think that that's another exciting area of academic research as well that I think is worthy of, that sort of fits under under this sort of academically dull applications heading, but for most academics. The good news is that right now, for every sensor that people put into their factory or put into their building at a cost of hundreds or thousands of dollars, there's at least another 10 that they'd like to have there that aren't sort of mission critical, but they'd still love to have the data. And so that's why in the short term, there's just going to be this huge rollout of sensors that don't get directly involved in the feedback control. But I think that's where the industry's headed.
So a few examples you mentioned that has to do with city government and public interest for sensor every block. At which cost point do you think this will become feasible? Putting on every block in San Francisco, that's going to cost a lot of money. It's $100 a piece right now. Right.
Yeah. What's it going to cost to put a sensor, every 5 meters on every street of every city of the world? It's going to be a huge expense, but you have to compare it to what they're doing with parking meters today. So the installed cost of a new parking meter in San Francisco is around $1,400, and the revenue, the coin revenue from that meter over its lifetime barely covers installation and collection of the coins and maintenance. So the reason that cities put in parking meters, there are two reasons. One is to get flow of get more bodies into the stores. That's number one. And number two is ticket revenue. So from an economic perspective, they love the ticket revenue. City of Berkeley, $7 million in ticket revenue in 2003. Big deal for the city of Berkeley. Right? They're always trying to optimize how much they can collect. City of New York, $500 million in ticket revenue in 2003. So these are non-trivial amounts of money for cities. And they're doing it, that's why they're spending $1,000 per meter to put it in. So if you can, so the answer is, $1,000 is probably an acceptable number for them to put it in for that particular application. I think Joe was first.
So, for me, one of the most sort of thought-provoking/radical things you said was the frequency hopping network configuration, the fact that you guys have gone back to a non-ad hoc networking model. I think it would be interesting over time to compare protocols where tactically everybody is a metric, and you start moving towards a much more carefully configured environment to application level things where maybe this isn't tactically not a metric, but this is a holistic measurement to the metric, and you need more ad hoc, more Scott, right? But this is the first one that's become a sort of essentially very limited there. Have you been getting pushback?
So summarizing the question is, Dust is using a centralized manager to make network decisions versus a distributed ad hoc, and what's the implications of that? So first off, the reason for that had to do with the pushback more than anything else. The companies that we were selling to did not want to hear about, ad hoc, distributed, stuff like that. I believe that the basic infrastructure of slotted, frequency hopping, links and digraphs and stuff like that, all that works fine with a distributed model. And we've got simulations that show the networks build fine. There's a little bit more churn because of, they don't have global view of interference and things like that. But I think it'll work fine for that. But the decision that we made early on was put it in a centralized manager, basically to make it more palatable, for the guys at GE and Honeywell and Johnson Control to wrap their hands around. It does limit you in terms of the size of the networks that you can build, and I think that our current approach, I can't see a reason why it won't scale to 1,000. And we're demonstrating it at 250. I have yet to take two of those networks and put them together just because we're sort of still going down the checklist to make sure all the things work. But I think it'll scale to something like 1,000 nodes per manager. In the building and industrial automation market, there really aren't any applications where it doesn't make sense to plug in another manager after you've got a few hundred nodes anyway. So that's fine for now. But I do think that you have a hard time building a 10,000 moat network with a centralized manager. So I think when we go, for applications where it is important to have really large networks, then I think it's got to be a distributed algorithm to make that work. The back corner was the first hand up.
I have a question about academically dull applications. Interesting terminology. So, do you think sensor networks are inherently academically dull? Or do you think that over time the application is somewhat sophisticated?
No, I think, I've basically I'm trying to come up with some way of capturing my frustration with the academic community and the fact that they've left this, what I feel is like the most important thing that we could be doing is building reliable networks that we can hand to people that want to use them, right? And we didn't do it in 2001 and 2002, and mostly we're not doing it today. And so there's the pain and frustration that I had going out and doing this stupid company was so that I could deliver these things, and I wish that I hadn't had to do that. I wish that as a community we had decided that it was important to not just feed ourselves, but actually hand things off to people and let them take them and run with them without having to become experts in TinyOS or whatever it was. So no, I don't really think that these are academically dull applications. I think they're fascinating, and I think that there's real meat in them from the hardware all the way up through the theory and everything in between.
All right, because of time,